So, welcome back, everybody. Just wanted to give you a quick reminder of where we ended last Monday, and what are the plans for the rest of the week. So, if we go back to the slides here, what we did on Monday was to give you a quick repetition of some of the basic properties of conservative forces. In the exercises which are going to solve now and also next week, we are going to drill a little bit more on conservative forces, non-conservative forces, internal forces, external forces. We're going to calculate things like the curl of a force. We are going to calculate the linear momentum, and we're going to see if it's conserved or not. And one of the things which we did on Monday was also to show the relation between a force and an eventual potential. So what we derived then was that the force is given by the gradient, the negative gradient of a potential. And this is extremely useful. Even if you don't have a fundamental law of nature, you can parameterize a force. And if you have a potential, which is the most common thing to do, actually, to parameterize a potential, you can then take the gradient of that one, and then you have an effective force between the objects which are at play, even if you don't have a fundamental force, because sometimes it's way too complicated to find a fundamental force. And we end up with effective forces. So if you're doing nuclear physics, it's way too complicated if you're dealing with protons and neutrons to start with the fundamental theory for the strong force, which is quantum chromodynamics. Then you would simply just have an effective force. Then, if we are dealing with materials, it's pretty common to use a technology which is called molecular dynamics. And there we need effective potentials between the particles. And these are actually set up by the underlying equations of motions, which could be the interactions between the electrons and the protons and so on. So what we're going to do today, however, is actually to practice a little bit and link what we discussed on Monday with the coming homework, and also seeing how we can use, let's say, the work energy theorem to derive, let's say, the positions or the velocities of specific objects. And then we are going to look at some other topics related to the homework. And this is how we actually calculate the curl of a specific object. So we have these two exercises, which we are going to do a little bit later today. So I'm going to lecture for something like 25 minutes. And then at the end of the lecture, we are going to look at how we can decide whether this is a conservative force or not. And when we go to the gravitational force, or this kind of force model, where this gamma is a parameter, this is something which is an object in 3 dimensions. And it becomes a little bit more, how to say, greasy to calculate the curl. But we are going to go through that as well. So you've seen the basic steps, and then you can apply them in the solution of the homeworks. Okay, so the problem we were looking at towards the end of Monday was a system, a pretty simple system. It was just a falling object, in our case, a falling ball, which is what we are doing in the homework. And in this particular homework, we are going to extend upon the program which we wrote in homework 3 by adding a contact force or normal force which acts from the ground on the falling ball. So when the ball hits the ground, in exercise in homework number 3, we just looked at a falling ball in a gravitational field and with some air resistance. Now we are going to look at how we can model a bouncing ball. So it hits the ground, and then it goes up again, and then it goes down again, up and down, till it comes to rest. So you might think that this course is about falling objects only. It's actually going to be a little bit more than that. But now we stay with these falling objects. Eh? You know, Galileo, he maybe we were too much inspired by Galileo, because he actually cooked up many of these relations by, according to legend, by looking at falling objects from the Leaning Tower of Pisa. Okay, so let's look at the example which we had. And the case we were looking at was a falling object. In our case, a falling ball. And we considered 2 cases. So one phase is an object which is falling from a initial height, which we just called y0, and then it falls down, and then it hits the ground. And this is y1. So this is when it hits the ground. So the way you can idealize the system now is it just hits the ground. And we just think of the moment before the normal force from the ground starts acting on it, okay? So in this specific case, what we had is this object, which is falling down. And this is under the influence of the gravitational force. So we have a force G, which is simply minus m times G. And in this particular case, we also know the distance between y0 minus h y1 is equal to h. So this is known, and we just put y1 equal to 0. So this would be the first case. And the question we can ask now, what is the velocity when it hits the ground? So in this case, notice now we haven't plugged in any time. So the only thing we have specified is the initial height. And we specified that it hits the ground. And we put that one to be equal to 0. So that's our choice of origin. So what we have then, when we look at the work energy theorem, so we have this work which is done from 0 to 1, which will then be given by y0 up to y1. And then we have minus m times g, which is the force acting in the y direction. So it's simplified. In homework number 3, you made a much more complicated case where you had an object falling in a gravitational field plus air resistance and falling in 2 dimensions. So in this particular case, we know that we can calculate. And since we put y0 to h, and we put y1 to 0, this is simply, when we calculate this one, this is mg times h. And this is supposed to be the difference between kinetic energy in position 1 minus kinetic energy in position 2. So in order to simplify things, what we are going to assume as well is that v0, we just put that to 0. So this is an object which is at rest and just falls down. And then we ask the question, what is v1? So when we use the conservation of, or the work energy theorem, and we have the relation between potential energy and kinetic energy, this will be 1/2 of m times v10, and then minus 0, since we put the kinetic energy in this specific case, which is 1/2 m times v0 squared, and that's obviously equal to 0. So from that one, we can then evaluate the velocity at the point y1, and this gives us simply plus minus of 2 times g times h. Now, if you think a little bit over what we are doing now, is that we are using the work energy theorem to find the velocity. We are not integrating up the acceleration to find the velocity, but we're actually using the work energy theorem. So this is an alternative in order to find the same quantity which we would get if we were to integrate over time. So they're just 2 alternatives, and depending on which one you choose, that is very much based on what the forces look like. So typically, if you have a force which depends only on the position, this is a typical approach which you would use. And then when you have the velocity, you could then integrate up again and find the position. But this is a typical strategy which you could end up using. Now, let's now look at the second phase. So what we assume now is that nothing happens with the ball, it just hits the ground. So if we now look at the ball which we have, what we could do now is to make a model. So this ball here has a radius, which we simply say r, and this is a known quantity. Now, as we discussed last time, this normal force is not a fundamental force, which means that we have to make a model for it. And we discussed a little bit back and forth on Monday, and we found that the spring force could be one way to model the normal force from the ground. So what we are looking at now, we are looking at this ball, which is at the position y1 equal to 0. And then it gets a little bit squeezed here. So let's just call it like this. So it has a distance r to the ground. We have the gravitational force, which is acting on the system. And then we have this normal force from the ground, F. And let's just call this an N here. So the net force, in our case, F net is equal to G plus N. Now, we are free now to model this kind of normal force. And one possible model for it is to now assume that this N, and this is the case which you're going to use now in the exercise. So you can think of this ball when it now hits the ground, that it is a little bit deformed. And this region of deformation corresponds to the overlap between the ball and the floor. So we are adding in some kind of deformation here. And what we are saying then is that this force could now be modeled as a minus K. And then we have an R minus Y. And this is now force which acts in the J direction only, in the Y direction. And we could say that this is equal to minus K of R minus Y multiplied with J when Y is less than this distance R and 0 else. Now, this is nothing but a model which we are making up now. So we are assuming now that when it hits the ground, it's in phase 1, it just reaches the ground. So Y1 is equal to 0. Then when it reaches the ground, in phase 2, it feels now the force from the ground, the normal force. And we are thinking of this as a kind of deformation of the ball, and that acts within a certain distance. And this is what you're going to implement in homework number 4. So when you take the program which you developed in the previous homework, the only thing you need to add now is a normal force from the floor. And you need to have an if statement where you say that if this distance, which it's been falling, is smaller or equal than this radius of the ball, then this normal force kicks in. If not, it's equal to 0. So when we now use this work energy theorem, what we could think of now is that in this phase 2, it starts at Y1 equal to 0, and then it goes up again. And it reaches a new position, which we might call Y2. And we don't know this Y2 here. And then we could ask, how far does it get before it stops? So suppose Y2 now is the position the ball has when it jumps up again, and then it stops. So just to simplify things, right? So we could now say that V2 here, just to simplify the calculation, is equal to 0. So it has a kinetic energy when it hits the ground. And then when it comes up to this Y2, it stops, and then it's falling back again, right? And this is what you're going to implement in homework number 4. In the program, you're going to have a ball which is just going up and down. And what you could say now is that when we want to integrate and we want to use the work energy theorem, we have the following. So we found that V1 is equal to this plus minus 2 times G times H. And then we are assuming also that this quantity H is known. We can also assume now that this parameter which we have in the force, this K, which we put in here, which is a material specific parameter, let's assume that that is known as well. So what we could say now is that this K is also known. So when we have that, then we could start integrating. So what we would start with, we also know that Y1 is equal to 0. And when we integrate now, what we would have is the following. So we would integrate from Y1 to Y2. We know that Y1 is equal to 0. We have chosen the origin to be there. So we have W1 from 1 to 2. And then we would have now the normal force. So we would have this N minus N times G of dy. And we know that this force, this normal force, acts only up to a specific distance r. So we would now have the normal force N, and now we can put it in here. So we have a K acting on r minus y, and then we have plus mg. of dy, but then the gravitational force keeps acting from r up to y2 here. And then we would have a minus mg times doy. So when we write it up, then what we get is minus k from 0 up to r. And then we have r minus y of doy. And then we have minus, and now I just can put it out here, mg from 0 up to y2. And then we have a dy here. And the assumption we've made is that y2 is larger than r. So we just made that assumption here. Then this is something which we can easily integrate up. So when we integrate it up, what we get is minus k, set in the limits, k times r squared, plus k times r squared divided by 2 minus n times g, times this quantity y2 here, which is the quantity we want to define. And then you see now that you can just rewrite it a little bit, and then you would find that y2 is equal to h. If we now put in the expression for the, let me just do one intermediate step here, I just forgot to do that. So this should actually be equal to 1/2 times minus v of 2 squared minus 1/2 of n times v1 squared. And we have defined v2 to be equal to 0. And we know that this one is just simply plus minus 2 times g of h, and then we have to square it. So if we do that, what we get is the following. So we get minus 1/2 of k times r squared minus n times g times y2 is equal to minus m times g times h, and h is the originally height, which the ball had. And then we can rewrite it and find what y2 is equal to h minus 1/2 times k times r squared, which is known, divided by n times g. So this is what you see here is a way to utilize the work energy theorem and find positions and velocities. Now, if you want to test your code with this specific force, what you could do now is just to let the object fall in the y direction, like you did in homework number 3. And then you could test whether this kind of analytical result matches what you see numerically. So that's always a useful test. So the analytical results are extremely useful in many cases, because if you can find analytical results, you can then compare your numerical results with the analytical results. Any questions so far? Too trivial, too simple? Okay, seems that this is okay. So the next thing I want to do is actually to move on to the 2 exercises we're going to look at today. But we are still going to stay a little bit with the work energy theorem, because I wanted to show you how we can go from the forces and find the potential energy. So one thing which we derived last Monday was the relation between the force and the potential energy. Now what we're going to do now is assume that somebody gives us a force, and then from that one we can use the work energy theorem to find the analytical expression for the potential energy. So let's look at how we can use that one. And we are now going to look at the gravitational force, because that's the one which we are going to take the derivative of just in some few moments. So let's look at the second example. And this is linked up with the exercises which we're going to do after I'm done preaching here. So we assume now that we have a force, which is simply given by a constant. So this could be the gravitational force, but it could also be the electromagnetic force. And this is squared. So just to remind you of that, so this R, when we write it like this, we will often write it just without the vectors. And in 3 dimensions, this is x squared plus y squared plus c squared. So in one of the exercises we're going to do pretty soon, we actually need to deal with a gravitational force or this specific force in 3 dimensions. You can obviously limit yourself to 2 dimensions. The calculations are basically the same. They are less complicated. So what we want to do now is to find the potential energy. So suppose now that we want to find the potential energy, when we now move from a distance r0 to a distance r1 minus gamma.
Excuse me?
Yeah.
What exercise are we currently looking at?
So this is an example actually, which we're looking at now. So
I'm also learning what the work energy theorem is, because all I can find in the textbook is the work kinetic energy theorem.
Yeah, that's the same actually. So the work energy theorem is normally also called the work kinetic energy theorem. So these are in a way synonymous. Okay, so let's continue a little bit here. So if you look at this expression which we have for the force, when you now look at this r times d of r, we can actually rewrite that one as a derivative, and we normally rewrite this in a compact way like this: 1/2 times r times r. And this is something which we did back in homework number 1. And we also know that r times r is actually r squared. So this is a number. So we can actually rewrite this as a d of 1/2 times r squared. And if we take the derivative of that one, this is something which ends up, because r vector times dr vector is also scalar, so just a number. So this is again equal to 1/2 times, sorry, we don't have the 1/2 because we are taking the derivative of r squared. So this is simply equal to r times d of r. So when we go back to the integral then, what we have is this w1, w0 to 1 is equal to minus gamma. And then I have an integral from r0 to r1. And then I'm putting in r d of r divided by r cubed. So this simply becomes minus gamma. And then I have an integral r0 to r1. And then I have a d of r. And then I have an r cubed here. No, sorry, r squared. And this is something we know how to integrate, right? Because we know the derivative of 1 over r gives us minus 1 over r squared. So we know that this one, when we integrate up, we should get 1 over r. So in our case, this is now equal to gamma divided by r. And then we have to take the limits r0 to r1. So in this specific case, what we end up with then is the following. So this is actually equal to when we put it in here, this gives us now minus gamma of 1 divided by r0 plus gamma of 1 divided by r1. Now, one thing we can do now is to decide that this r0 is our distance relative to a specific origin. So that means that we know that specific value. So we could say that r0 is our origin. We know that value, and that means that we could actually rewrite that in terms of a new quantity, which we just simply call v of r0. And this is often written just as v0. So remember now that these potential differences and energy differences, they are always calculated with respect to some kind of origin, right? So this is something which we in a way are free to define. Then what we do next is that this gamma of 1 divided by r1 is something which we now define as minus v of r1. And I will come back to why we define this minus v here. And then we are going to make this more general. So we're going to say now that r1 goes over to a just general variable v of r. And that means that in our case, we have a v of r, which is equal to minus gamma divided by 1 over r. So this is a scalar. And then we remember that f of R is given by the gradient of this potential V of R. So when I now have the potential itself, I can calculate the gradient. And now we have to be a little bit careful because now we need to look at the expression for the potential here. And this is where you have to pay a little bit attention because now what we need is actually to calculate, in this specific case, minus gamma. And then we have a d dx of I. This is the vector. So d, we are setting up the expression for the gradient here, plus d dz multiplied with the vector k. And then we have to take the derivative of 1 divided by r. And 1 over r is equal to 1 divided by x squared plus y squared plus c squared. And if we now take the derivative of this quantity, if we take the derivative, for instance, in the x direction, so the reason why I'm setting this up now is that when you are going to do this exercise today, which we have on the slides, you are going to take the curl of the force, and then you need to take these derivatives. So if you have the derivative with respect to x is actually the derivative of this quantity here. So that's x squared plus y squared plus c squared. And if we now just use the standard rules for derivatives here, we know that this has to be equal to, we get a factor of a half. So we get 2x, and we have a factor of 2 here. And then we would get x squared plus y squared plus c squared. And this is to the power of 3/2. And then you would do the same thing with the y direction, d dy, of the same quantities. I'm just putting a repetition sign here. And then I would simply get y divided by x squared plus y squared plus c squared to the power of 3/2. And this would just continue with dz. And we will get z divided by x squared plus y squared plus c squared to the power of 3/2 here. Then what we do next, we go back to what we had here. So we have the expression here. So this is a quantity we're going to look at. So we have a vector in the x direction, a vector in the y direction, and one in the z direction. So now we just took the derivatives with respect to the quantities. So we have taken the derivatives, but now we need to add the vectors here. So when we add everything up here, what we get is the following. So that means that this quantity here, f, which is equal to minus del of v of r, becomes equal to minus gamma. And then I have now x times I divided by this quantity x squared plus y squared plus c squared of 3/2. And then I get a plus of y times the vector in the y direction. And now I'm just getting lazy. So I just put dots in here, right? It's the same here. And then plus c times k divided by this quantity to the power of 3/2. And this is nothing. When we now collect everything, we have the minus gamma, and then we have the vector r, and this is divided by the quantity r cubed. And this is where we started. So we started with that force, and then we used the work energy theorem to find the potential. And then we went the other way back, and then we found that what we started with gave us the potential. We used the expression for the relation between the potential and the force, and then we found the same force again. So there is some kind of system in the craziness here. Now, the reason why I brought this up is that in this small exercises we're going to do today, we actually need to prove. So what we showed now is that F is equal to minus, if we have a potential which depends only on the position. That's the interesting quantity here. So the thing we are going to look at next, in order to show that this is a conservative force, is that this quantity is equal to 0. So that means that when you take the curl, what you would need, if you now look at the curl in the x direction, just to remind you of that, before we jump onto the exercises, if you take that one in the x direction, this is simply equal to d dy, and then I have the derivative of the force in the z direction, minus d dz of fy, and this is multiplied with the unit vector in the x direction. And then you would have similar expressions for the curl of the force in the y direction and in the z direction. So these are the quantities you now need to look at in order to decide whether this is a conservative force or not. And the nice thing, if you can decide that the force is conservative, you can simply state energy has to be conserved. And when you're running something numerically, then that is an extremely important test that your numerics is functioning correctly, because then your energy should be conserved. And if it's not conserved, then your numerical implementation is wrong. Or if we insist on using Euler's method, you're going to get an energy which is not conserved over time. And that's one of the failures of Euler's method, which you are going to implement next week on the Earth Sun system. So next week, we need to modify a little bit Euler's method so we can conserve energy as a function of time. So that's an extremely useful test. So if you develop an algorithm which does not conserve energy and you have a conservative force, then something is going to go wrong and you're going to make wrong predictions. Hopefully nothing wrong happens except that you get the wrong results. But in some cases, this can actually cause accidents. And there are many cases of algorithms which have gone wrong because people didn't make tests like this, unfortunately. So this is an extremely useful test. And then now we are going to use the rest of the lecture here. And we're going to go back to these two small examples, which we put up in the slides here. So one is to calculate so in both cases, we have forces which are dependent only on position, but you need to show that these forces are conservative ones by finding the curl of the forces, that one is actually equal to 0. So the first one, you should almost not need any calculations at all because you have a one-dimensional object. And a one-dimensional object, when you take the curl of that one, that is equal to the roundest number you can think of. But the other one, you have to convince yourself that the gravitational force or that type of force is actually a conservative one. So I'm going to stop the lectures, and then Julie and George and myself, we are just going to move around. George will take care of the people which are online, and Julie and me will just float around. Feel also free to ask about other exercises for the homework. Okay? Don't feel constrained that you only have to do what we say here. So if you've done that one, you can always ask about the homework, right? Any questions so far? We just sit down and calculate a little bit. I'm just going to switch off the recording as well. I'm going to leave that one here.